pretty good. Of course, it depends on the application and the time scale. If the time scale is like years, and the application is, I don't know, figure out something about social networks, a year might be too long. So we think that the method does pretty well, but this is just our first cut. I think that if you tried, given what we learned here, we can probably do slightly better and maybe try to reduce that time frame down to maybe 2 networks or so. But it really depends on trying to characterize just how big that change is across the change point.
Just a brief follow-up.
OK.
In terms of determining your difference of networks here, do you have guidelines as to how to represent the data in order to make that kind of a sharper distinction? I mean, are there guidelines for the representation, the encoding, or however you want to characterize that? I'm not really clear about that.
There's not much guidance, I would say. A lot of it is intuition. There's a sort of an art to doing it well. You can turn it into another inference problem. So for instance, if I have time series data on the per minute resolution, and I don't know at what level I should bin the data, I could run this analysis at all different ways of binning it, and then ask some question about which one does better under some objective function. But you still got to define that objective function, and we don't know which one to choose, and so on. Yeah.
So I actually wanted to ask you this upfront when we were showing those block diagrams, right?
Yep.
Unless you solve a graph isomorphism problem, you would never get those block structures out from your matrix anyway, right? Because you would have to commute the vertices to observe that. How did you deal with this on the examples that you actually showed us where you have done this kind of analysis?
So two points I want to say. One is that each of these block matrices is another network, right? So now it's a weighted network where in its